Hi, this lesson is about vectors. But before we can understand vectors, we have to talk about scalars. So scalars are quantities, and quantities have a measurement that we call a magnitude. Examples of scalars would be length, area, temperature, speed. Those are all things that you can measure. And there's many other examples like height and weight, and I'm sure you can think of many others. Vectors are quantities with both magnitude and direction. So, direction means you know the direction that the particular magnitude is coming from. So, for example, 60 miles per hour in a direction 25 degrees west. So, you not only know the speed of the object, but you also know that the direction it's coming from. So some examples of scalars and vectors are here. Example 1. We have part A, a small craft warning reports winds of 25 miles per hour. Well, that's just telling you the speed of the wind, so that's just a scalar. Part B says a small craft warning reports winds out of the north at 25 miles per hour. Well, out of the north, that's telling you the direction that the wind is coming from, in addition to the speed of 25 miles per hour. So part B is a vector. Part C says a ballistic test shows that a bullet hit a wall at a speed of 400 feet per second. So again, that's just how fast the bullet is traveling. That's just a scalar. And part D says a ballistic test shows that a bullet hit a wall at a speed of 400 feet per second, perpendicular to the wall. Well, that's telling you the exact direction that the bullet was coming from when it hit the wall. So it has both a magnitude and a direction, and therefore D is a scalar. So the first half of this section, this video lecture, we'll talk about vectors from a geometric perspective. So let's talk about how to represent vectors. So a vector is basically going to look like an arrow, like what you see here. It has an initial point, which is where it starts, and the initial point is where you call the tail. So this would be the initial or starting point of the vector. The ending point or the terminal point is at the head. The head is represented with an arrow. The magnitude, when you're talking about this from a geometric perspective, it's basically going to be the length of the vector, although magnitude could be other things other than length. But when you're graphing this, this is going to be your length. And the direction is the angle that the vector is traveling in. So if you can imagine like a horizontal line here, my direction would be the angle created by the vector and the horizontal line that comes out from the initial point. Okay, so there's lots of different notation for vectors. So if I call the tail, or my initial point A, and my the head or the terminal point B, then you can say that the magnitude or length of the vector is what you see here. And this is not an absolute value, it's just notation. Other common notation, and these would mean the same thing, would be instead of single bars, they use double bars, and I've used both throughout this lecture, but they mean the same thing, and this would be the magnitude. Magnitude or length of the vector. Okay, so typically if you're looking at textbooks, vectors are represented by bold-faced notation, but for writing purposes, because it's kind of hard to make things look bold when you're writing, we just put a little arrow on top of the name of the vector. This means vector u, and this means vector AB. And if vector u has an initial point at A and a terminal point at B, it would be representing the same vector, just with two different naming conventions. Okay. So, additions. So we can add vectors. So there are two geometric ways to represent that addition of vectors. So I'm going to show you both the polygon method and the parallelogram method. And either way is fine. You get the same result. So with the polygon method, if you're adding two vectors, let's call them u and v, the first, to represent the addition of the two vectors, you connect the tail of the second vector to the head of the first vector. So if u is the first vector and v is the second vector, the tail of u gets connected to the head. The tail of v gets connected to the head of u. Then the resultant vector, which is our sum, right? So we'll call it r. If u plus v equals r, then the resultant vector is the result of connecting from the tail of the first, which is here, to the head of the second. So u plus v is represented by this green line on the picture. Okay, in that, the resultant vector r has its own magnitude and direction, which is different than u and v. Okay, so look at this from the perspective of the parallelogram method. With this method, the u and the v vectors are going to represent two sides of a parallelogram. Remember, a parallelogram looks like a rectangle that's kind of pushed on its side, so it has four sides. So u and v are two sides of the parallelogram. And you connect the tail, so this would be the tail of u and the tail of v get connected at this point right here. Then you draw two lines parallel to u and v. So parallel to v is this one that you see here. And parallel to u is this one that you see here. And when you connect them, you end up with a parallelogram. The resultant vector r, which is u plus v, is just the diagonal that goes from where the two tails started to the opposite end of the parallelogram. So it's the diagonal across the parallelogram. So if u and v in these two pictures have the same magnitude and direction, and they are supposed to be the same, u plus v is actually the same resultant vector in both the polygon method and the parallelogram method with the same magnitude and direction. Okay, so multiplication of vectors by a scalar. A scalar, remember, it's just a number, it's a quantity. So if we let c be our scalar, and it's a real number, and v be our vector, then cv creates a new vector with the following characteristics. So the magnitude of this new vector cv would just be the absolute value of c, because c could be negative, times the magnitude of v. Remember, this represents the magnitude of v. So if number, when you take the absolute value, if the absolute value of c is greater than 1, it will make the vector v longer. If the absolute value of c is between 0 and 1, it will shrink. The length of v, or the magnitude, will get shorter. So if c is a positive number, then the direction of cv goes in the same direction as v. If c is a negative number, then it's going to make it go into the opposite direction. It will basically flip the direction of the vector. If your scalar is 0, well, c times v is just going to give you a vector 0, which means it has no magnitude and no direction. So here's kind of a picture of what would happen if we multiplied by a scalar. Suppose this is the original vector v. If you multiply the original vector v by negative 2v, so it doubles the length of the vector, so this is twice as long as v, but it's also going in the opposite direction. So the tail is up here and the head is down below, which is the opposite of what you saw with v. And if you take 1/2 of v, well, 1/2 is a positive number, so the direction is the same, but the length of vector v is half of what 1/2 of v is half of vector v, the original vector. Okay, so let's move on. So here, I'm basically saying that when you are subtracting two vectors, well, it's the same as addition, because you can multiply vector v by -1, and so u minus v is the same as u plus -1v. All right, so vectors can also be described analytically by using something that we call components. So every vector is made up of what we call an x and a y component. And so there'll be different notation to represent these vectors. This will be the first one that we'll use. We say vector v is equal to, and these are not parentheses, these are actually kind of pointy parentheses, if you will. So vector v is equal to the components a sub 1 and a sub 2. These are considered to be the horizontal component of v and the vertical component of v. So sometimes instead of calling it horizontal and vertical, I might call them the first one the x component, and the second one I might call the y component, but they mean the same thing. Okay, and the reason this works, just from a geometric perspective, if I have a vector v, and I'm going to draw it here in quadrant 1, but vectors could be anywhere. So if this is vector v, in order to go from the initial point here, which I made the origin, to the terminal point here at the head, I had to go over a certain number of units to the right and a certain number of units up. So the number of units that you travel to the right, well, that's what we're calling our horizontal component, and the units that you traveled up, that's what we're calling our vertical component. So you have an initial point, a terminal point, but the components are made up of the distance traveled from initial to terminal, both the horizontal and vertical distance. All right, but how do you figure those out? Well, there'll be more than one way to figure those out. So one way is if you know the initial point, and I'll call it point P, and if you know the terminal point, and we'll call it point Q, if point P has coordinates x sub 1, y sub 1, and point Q has coordinates x sub 2, y sub 2, then the x component, or the horizontal component, would be the difference of x sub 2 minus x sub 1. So this is a sub 1. This is the horizontal component. And the second one, the vertical component, or the y component, which we call a sub 2, would be the difference of y sub 2 minus y sub 1. All right, so let's use this information. We want to find the component. We're here on example 1. Find the component of the form for vector u with an initial point of -2, 5 and a terminal point of 3, 7. All right, so according to the formula that I just gave you right here, you have to take the x value of the terminal point, which is this one, and the x value of the initial point, which is the -2, and subtract them. So that's what you see here. So it's 3 minus -2, which becomes 5. So that's the x component of u. Then to find the y component of u, you repeat this process. So I'm going to take the y component of the terminal point and the y component of the initial point, subtract them. 7 minus 5 gives you a value of 2. So vector u has components 5, 2. All right, so let's look at this next example. It's similar, but different information is given. You're given that vector v has components 3, 7. So you're basically already given what the components are. And you're also told that the initial point is 2, 4. The question is, what is the terminal point? Where is the head of the vector? So if I use the formula that a sub 1 is equal to x sub 2 minus x sub 1, and a sub 2 is equal to y sub 2 minus y sub 1, well, that's exactly what I did here. I have 3 is equal to x, which is my terminal point. I don't know what it is. I'm trying to figure it out. Minus my initial point, 2. And 7, which is the y component right here, is equal to y minus my initial y value. And then I just solve both of those equations for x and y. So here you get x is equal to 5 and y is equal to 11. That represents the terminal point 5, 11. So it's a vector with an initial point of 2, 4, a terminal point at 5, 11, and its components are 3, 7. Okay, so if you do know the components, you can easily find the magnitude and the direction of the vector. So the magnitude, if you're told that vector v has components a sub 1 and a sub 2, the magnitude, which I'm indicating here with this double line around the v, the magnitude or the length of the vector is the square root of a sub 1 squared plus a sub 2 squared. And that's actually not a new formula for you. That's actually your Pythagorean theorem. So I'm going to create a vector here. Let's say this has components a sub 1 and a sub 2, as I described before. And the length of the vector would essentially be the hypotenuse of this right triangle that's created when you extend the vertical line down to the x-axis, and that's your a sub 2. So normally we call this C if you're using the Pythagorean theorem. We called it R when we were dealing with our unit circle. So what we would normally call R, I'm now going to call the magnitude V. And so we know that a sub 1 squared plus a sub 2 squared is equal to the hypotenuse squared. And when you take the square root of both sides, well, you get exactly what's in the box on the right. And so your magnitude V is a sub 1 squared plus a sub 2 squared, which is this. Okay, so anything in a box you would want to memorize will make things easier for you when you get tested. And the direction should also be somewhat familiar for you, because remember, the direction is the angle here created by the vector v and the horizontal line, which in this case is our x-axis. And so if you know components a sub 1 and a sub 2, then the appropriate trig function to use would be tangent, because tangent is opposite over adjacent. And so opposite of theta is a sub 2, adjacent of theta is a sub 1. But again, the direction means that you're solving for the angle, and so your theta would be tan inverse of a sub 2 over a sub 1. Okay, Usually we're working with degrees with vectors. If you're ever using a calculator to help you get your direction, you would have to be in degree mode. All right. So let's talk about using the formulas for magnitude and direction. So I want to find the magnitude and direction of both of the following vectors. So part A says that u has components 2, -3. So let's do part A first. So the magnitude is here. The magnitude of u will be the square root of 2 squared plus -3 squared. When you square those and add the numbers, you get square root of 3. Square root of 13. Square root of 13 is an exact answer. If you were asked to round it, you'd have to put it into a calculator and round appropriately. So now let's find direction. We're going to use this, that theta is equal to tan inverse of a sub 2 over a sub 1. In other words, the y component over the x component. So I have tan inverse of -3 over 2. And if you put that into a calculator, it would give you a negative result, which you don't want. You always want to express your angles as positive angles in the appropriate quadrant that you belong in. Now, how do you know which quadrant you belong in? Remember, think of this as like your x and y values. When your x is positive and your y is negative, that means you are in quadrant 4, which means that your angle here must be in quadrant 4. So whatever angle you get as your reference angle, you subtract 360 minus the reference angle to get 303.7 degrees. All right, so we'll do the same thing for V. Vector V has 2 components that are fractions, which is fine. So I have that vector V has components -3/5, +4/5. So this is in quadrant 2. First component is negative, second component is positive. So when your x is negative and your y is positive, you're in quadrant 2. All right, so magnitude first. I'm going to take the square root of -3/5 squared plus 4/5 squared. That's 9/25 plus 16/25. Well, that's just 25 over 25, which is 1. So it has a magnitude of 1 unit. Okay, so that's done. Now we have to take tan inverse of the y component over the x component. So my x component got cut off here. So I have tan inverse of 4/5 divided by -3/5. And when you work that out, you get 126.9 degrees, which is good news because that is in quadrant 2, and you have found all of the required information. Okay, and remember, when you're looking for your angle or your direction, make sure you're in degree mode when you're working with vectors. All right, so here's some algebraic operations on vectors. If you have these are some properties. So if you have 2 vectors, u and v, where u has components a sub 1 and a sub 2, and v has components b sub 1 and b sub 2, then if you add the 2 vectors, it's the same as adding the individual components. So notice that u plus v, the sum of that will have components a sub 1 plus b sub 1. In other words, the corresponding x's get added, and then y components a sub 2, b sub 2, so the corresponding y values get added. The same is true for subtraction. So vector u minus vector v just means that you subtract the corresponding x components and the corresponding y components. And then c times u, where c is a real number, so any number, positive, negative fraction, could be 0. Multiplying a vector by a scalar just means that each of your components get multiplied by that same scalar. So you get c a sub 1 and c a sub 2 as your horizontal and vertical components. All right, so we're going to use those properties or operations. So here, example 4, if u equals 2, -3, and v is -1, 2, we want to find each of the following. So we'll start with A. A says that we're going to add u and v. So here's the work. You add the corresponding x values. So I have 2 and -1 right here, and that gives me 1. And then I have -3 and 2, which is here, and that also reduces down to just -1. So my sum has components 1, -1. Okay, so let's do part B. Part B says that I'm subtracting. So it's the same numbers that we used before, except we are subtracting them. 2 minus -1, -3 minus 2 gives us the components 3, -5 right here. Part C is asking us to do 2 times u. So remember, 2 is a scalar, and it's getting multiplied by vector u, which means that both components get multiplied by 2, and that's what you see here. So the result is components 4, -6. Third example is asking us to multiply v by -3. Okay, so same idea. Take vector v and take both of the components, multiply them by -3, and you get the result of 3, -6. All right, so now we're on the last one, 2u plus 3v. So we're using all of the properties. We're multiplying each vector by a scalar and then adding those results. So 2u plus 3v, that's what you see here. I have to multiply vector u by 2, vector v by 3. That result is in the second line in that problem. So we get 4, -6. It's being added to -3, 6. Then we add the corresponding horizontal components, or the x's. So 4 and -3 gives me 1, -6 and 6 gives me 0. So 2u plus 3v has a vector value, component value of 1, 0. Okay, so here are some other properties that are helpful to know. So the first few should look familiar to you. So the first one says that vector u plus vector v is the same as vector v plus vector u. That's like your commutative property for a lot of things that you do in algebra. The second one says that vector u plus the sum of vector v plus vector w is the same as the sum of vector u plus vector v plus vector w. So the second one should remind you of the associative property. The third one, vector u plus vector 0, well, that's like the identity property of addition. It doesn't change vector u. Vector 0 has no magnitude, no direction, so it's just equal to u. And vector u plus negative vector u, remember that means that u is going in the opposite direction, and when you add two vectors with opposite signs, they basically work out to just be 0. Okay, so like the inverse property of addition. Here's some other properties that should look familiar to you. So if I have a scalar c multiplied by vectors u and v, that's cu plus cv, like the distributive property. Similarly with the second one, if you have two scalars, c plus d multiplied by vector u, that's the same as c times vector u plus d times vector u. And number 3, again, should remind you of associative, because you can group them in different ways. So if you have CD, C times D times U, you can multiply CD and then multiply by U, or you can multiply D and U and then multiply by C, or you can multiply C and U and then multiply by D, and they all give you the same result. 1 times vector u is just u. 1 doesn't change the vector. Magnitude or direction stays the same, so that's like the identity property. 0 times vector u is just 0. And c times vector 0, that's also just 0. All right, so now let's talk about unit vectors. So there's a lot of vocabulary in this section, so you might want to go over this again when we're finished. So a unit vector is a vector of length 1. So remember, length is what we call magnitude, and we have two special notations for these vectors of length 1. We have vector I, which is usually represented with a bold-faced I, but it could also be written like this. And then vector J could also be written like this. These are read as I hat and J hat, because it looks kind of like they have a little hat on them. So unit vector I has components 1, 0. Unit vector J has components 0, 1. So unit vector I is associated with the horizontal component because the y value is 0. And J is associated with the vertical component of a vector. So this will allow us to now introduce new notation. If we have a vector u represented as 5, negative 8, when we write that in terms of ij, that means that vector u is equal to 5i minus 8j. And this is called ij format. And this one above is called component format. But they mean the same thing. Okay. So if u, we're here on example 6, if u equals 3i plus 2j and v is equal to negative I plus 6j, we're going to write 2u plus 5v in terms of ij. So we're going to be using the properties we talked about above. We have scalars multiplied by vectors and we're adding, but we want to represent our answer in ij form. So vector u gets multiplied by 2, which is what you see here. Vector v gets multiplied by 5, which is what you see here. So both components get multiplied by the scalar. So I get 6i plus 4j, and then I get negative 5i plus 30j. Now, to represent the sum of these two vectors, you're just you're just adding the corresponding components. So you can also think of it in terms of like terms. You combine the 6i with the negative 5i, which gives you I, and you combine the 4j with the 30j to get 34j. So the sum is the component I, 34j. In component form, you would write 1, 34, right? Because the coefficient of I is 1 and the coefficient of j is 34. Okay, let's talk more about components. So if we let v be a vector with magnitude v, and remember this notation means the same as this notation. This is magnitude. So if vector v has a magnitude of v and a direction of theta, then you can find the components a sub 1 and a sub 2 with these two formulas right here. So a sub 1 is the magnitude times the cosine of the angle. That gives you the horizontal component. And a sub 2 is the magnitude times the sine of the component. And that gives you, times the sine of the angle. And that gives you the vertical component. So once you figure that out, you can resolve it and be able to state that your vector is v cosine of theta I plus v the magnitude sine of theta j. So where did this formula come from? So it comes from trigonometry. So I'm just going to kind of remind you of something that you already know. So again, if I have a vector v, this is v, with components a sub 1 and a sub 2, and you're told that you know the magnitude and you know the direction, and you need to find a sub 1 and a sub 2. Well, if I needed to find a sub 1, and I knew the magnitude and direction, then the appropriate trig function would be cosine, because cosine of theta is adjacent over hypotenuse, which is the magnitude. Then if you solve for a sub 1, you multiply both sides by the magnitude, so you get magnitude cosine of theta equals a sub 1. That's the first formula right here. Similarly, if I knew the magnitude and direction and I wanted to solve for a sub 2, then the appropriate choice would be sine, because sine is opposite over hypotenuse. And if you solve for a sub 2, you multiply both sides by magnitude, and you get this formula, which was the second one that I stated. Okay, so it's all based on things that you learned from trigonometry. All right, so let's do example 7. A vector v has a length 8 in the direction of pi over 3. So this is expressed in radians, which is fine. Find the horizontal and vertical components and write v in terms of your ij format. All right, so a sub 1, remember, it's your magnitude, which is 8, and the cosine of the angle, which is pi over 3. Remember, pi over 3 is 60 degrees. 60 degrees is a special triangle. This is 60, this is 30, and this is 90. Opposite of 60 is root 3. The hypotenuse is 2, and opposite of 30 is 1. So the cosine of 60 degrees is 1/2, which is what you see here. So 8 times 1/2 gives me an x component of 4. Similarly, I have to find a sub 2, and remember the formula for a sub 2 is magnitude times the sine of the angle. So it's 8 times the sine of pi over 3, and the sine of pi over 3, or the sine of 60 degrees, is root 3 over 2, and when you simplify it, you get 4 root 3. So the way you express vector v in component using the ij format to express its components, you have that v is equal to 4i, which comes from here, plus 4 root 3j, which comes from here. Okay, so again, as I mentioned before, you're going to want to memorize this formula. I'm just going to put it in a box to make that more obvious. You want to know how to find components of a vector if you know its magnitude and direction. All right, so here's another example in degrees. We have vector u that has a magnitude of 42 and a direction of 210 degrees. 210 degrees is in quadrant 3. And if you're in quadrant 3, that means that my x and y components, my horizontal and vertical components, must both be negative. All right, so we're going to find the components. So a sub 1 is 42 times cosine of 210. So 210 is actually a special angle because when you figure out the reference angle, it is 30 degrees. And that's because, put that over here, 210 minus 180 is 30 degrees, and that is your reference angle. Since that's 30 degrees, here I have a value of -1. Here I have a value of negative root 3, and this is a value of 2. So that's, again, that triangle that I asked you to memorize many times. So the cosine of 210 is adjacent over hypotenuse, so that's negative root 3 over 2. And when you simplify that, multiplying by 42, you get that the horizontal component is negative 21 root 3. Okay, so now let's find the y component. y component is a sub 2 is 28 times the sine of 210. And again, we look back at our triangle here. The sine is opposite over hypotenuse, so that is negative a half. And when you simplify, your y component is negative 21. So when you express this in component form, like we were asked, this is negative 21 root 3, comma, negative 21 with these pointy brackets around the components. Okay. Here in this next example, you're given the vector u equal to negative root 3I plus j, and you're being asked to find the direction. This time the components are known. When you know the components, we have to go back to one of the formulas I mentioned before, and that is that the tangent is the y value, the y component over the x component. So in this case, that'll be 1 over negative root 3. And we know that we are in quadrant 2 because the x component is negative and the y component is positive. So negative x and a positive y means you're in quadrant 2. All right, so if you were to do this in radian mode, you would get a value that would be negative, and you would have to figure out what that is, and then use that to get into the appropriate quadrant. So 1 and root 3 should be numbers that should kind of sound off in your mind. Oh, I should know these, and actually we used it a couple of times. Tangent is opposite over adjacent. So that's where the 1 and the negative root 3 comes from. And when you have that combination of numbers, your hypotenuse is 2. So that means that this is 30 degrees. But if I express that in radians, that is pi over 6. That's your reference angle. But I don't want the reference angle. I want the quadrant 2 angle. So what you do is you take pi minus pi over 6, which has to be rewritten as 6 pi over 6 minus pi over 6, which gives you an angle of 5 pi over 6, which is your answer. Okay, so let's use some of what we learned and apply it to a couple of word problems. So here's the first one. It says, a man pushes a lawnmower with a force of 30 pounds exerted at an angle of 30 degrees to the ground. Find the horizontal and vertical components of the force. All right, so the man that is pushing the lawnmower, so here's the lawnmower. In order for this lawnmower to move and cut the grass, presumably, the lawnmower must move forward as well as being pushed down. So there's two forces acting on this lawnmower to get it to move. So the force that will make it move forward is our horizontal component, and the force that'll push it downward so that it's actually cutting the grass and making pressure along the ground is our vertical component. So the magnitude is the force that the man is exerting on the lawnmower, and the direction is the 30 degrees. And to the ground will be important because we know he's pushing downward. So the horizontal component, I have a sub 1 equals 30 times cosine of 30 degrees. All right, so we just worked with 30 degrees. The cosine of 30 degrees is root 3 over 2. So 30 times root 3 over 2 is 15 root 3. That's the horizontal component of his force. All right, now we have to find the vertical component. And the vertical component will be the magnitude times the sine of the angle. But notice that here I put a negative in front. And that's where this is important. He's pushing to the ground. Pushing to the ground means that he's standing, he's pushing down. The force is going downward. So that downward direction has to be indicated with a negative. So I have negative 30 times the sine of 30 degrees. Sine of 30 degrees is a half. So your vertical component is just negative 15. Okay, so let's do another one. This one is a little bit more elaborate, more interesting. So example number 11, and it'll be the last one for this lesson. It says that a woman launches a boat from the shore of a straight river that is flowing east at 5 miles per hour. She wants to land at the point that is directly opposite of the river to where she starts off. If the speed of the boat relative to the water is 10 miles per hour, what direction should she head the boat in to land where she wants to land? Okay, so this one's a little tricky because the boat's on one side of the river and she wants to go directly across. She doesn't want to go at an angle across from where she is. She wants to be directly across from her line of sight. But the river, when she pushes off, the river's going to push her in this direction because it's traveling east. So in order for her to land across, she can't start off going perpendicular to the river. She has to start off going at an angle away, going westward from where she wants to land because the river is going to be pushing her along. All right, so let's see how we figure this out. We're going to let u be the velocity of the river, the vector component of the river, which will have both magnitude and direction. And we're going to let v be the velocity of the boat, which again will have magnitude and direction. So because the river is only traveling eastward, we only have one component, the horizontal component. There is no vertical component. So u is 5I, or you could also write it like this, 5, 0. But v, now v's a little bit more complex because we don't know what the components are of the boat because she's not traveling perpendicular to the river. She really has to travel at an angle. So I need to figure out what that is. So I have my v is 10 cosine of theta I plus 10 sine of theta j. Remember, 10 cosine of theta is the horizontal component, and 10 sine of theta is the vertical component. And I want to know what happens when both the river and the boat are working together to get to where they have to be, which means we are going to be adding those two vectors together. So I'm going to call that W. So W, vector W, is the sum of U plus V. So remember, when you're adding vectors, it's like adding like terms. So I have vector U is 5I. I have vector V is 10 cosine theta I and 10 sine theta j. So when I combine the i's, I get 5 plus 10 cosine theta of I plus 10 sine theta of j. Okay. So remember, she wants to land the boat directly across from where she landed. So that means that her horizontal component has to equal 0. She basically wants to go vertically. So that means that she doesn't want to move horizontally from where she started off. So I'm going to take my horizontal component and set it equal to 0 and solve that equation. All right, so when I solve that equation, you subtract 5, divide by 10, simplify, you get cosine of theta is -1/2. So again, those numbers 1 and 2 should look really familiar because that's adjacent and hypotenuse. So that's going to be a 60-degree triangle, which is what you see here. But we have to keep in mind our component. So our components, remember, where's my picture? My component, almost figure it out from here. If I need to go a little left in order to go across, that means that my angle has to be in quadrant 2, because quadrant 3 means you'd be going in the opposite direction. Same thing with quadrant 4. And if you go into quadrant 1, the river is going to push you way out here somewhere, and you don't want that. So you really have to consider your angle being in quadrant 2. So when I figure out that my angle is 60 degrees, and seeing that you have a negative, cosine is negative a half, cosine is negative in either quadrants 2 and 3, and as I explained, quadrant 3 would be impossible because you'd be going backwards, so it has to be quadrant 2. So the angle would be 180 minus 60, which is 120 degrees. And in terms of like something really practical, that means that the woman would have to travel in the boat going north towards the other side of the river, 30 degrees west, so that she can end up directly opposite. Okay, so now you should be ready for the homework. Good luck.